Graphing rational functions. A rational function is any function that can be written in the form f of x equals p of x divided by q of x, where p of x and q of x are polynomials, and of course q of x cannot be equal to 0. So as an example, the function f of x equals x minus 4 over x minus 2 is a rational function because x minus 4 is a polynomial and x minus 2 is a polynomial. So let's go ahead and find some function values. So first, let's find f of 0. Now remember, this just means plugging 0 in for the value for x. So that's going to give us 0 minus 4 divided by 0 minus 2, which is negative 4 divided by negative 2, which is positive 2. F of negative 4, same idea. We have negative 4 minus 4 divided by negative 4 minus 2. This is negative 8 divided by negative 6, which simplifies and reduces to positive 4/3. F of positive 4, similar. We're going to have 4 minus 4 divided by 4 minus 2. This is 0 divided by 2, which is equal to 0. F of negative 2 is negative 2 minus 4 divided by negative 2 minus 2. And this is negative 6 divided by negative 4. And that reduces to positive 3/2. And finally, the most important one, f of 2. F of 2 is 2 minus 4 divided by 2 minus 2. And this is negative 2 divided by 0. And this is the most important one because we cannot divide by 0, which means that this is undefined. And what that means, since when you plug in 2, you get undefined, it means that this number here, 2, is not in our domain. So let's briefly talk about the domain of a rational function. The domain is going to consist of all values of x that you can plug in where you do not get division by 0. So another way to think about it is all numbers except for the numbers that make the denominator 0. Now, since the denominator here is x minus 2, the only number that makes that 0 is x equals 2. So the domain is going to be all real numbers except 2. And the way we can write that is all numbers from negative infinity up to positive 2, not including, union all the numbers from 2 up to infinity. In our next example, we want to compare the graphs of the equations y equals x squared minus 9 divided by x minus 3, which you can see is a rational function. And how is this graph different from y equals x plus 3? Well, y equals x plus 3, this is simply a line, right? So what is it about y equals x squared minus 9 divided by x minus 3? Well, what you should see here is that if you simplify this, you can factor the numerator into x minus 3 times x plus 3. And you can you can leave the denominator as is, and then you can cancel the common factor of x minus 3. So when you simplify it, you get y equals x plus 3. However, there is a catch. Since this function started with x minus 3 in the denominator, you are not allowed to plug x equals 3 in here because 3 take away 3 would be 0. And that means that you are not allowed to plug 3 into its simplified version as well. So even though technically there's nothing wrong with plugging 3 in here, right? Clearly you can see if you plug in 3, 3 plus 3 is 6. But because this is considered to be the simplified version of this, we have to maintain whatever restriction this function had over in our simplified version. So what do they look like? Well, again, y equals x plus 3 is just a line. This is also y equals x plus 3, which is also a line. However, x cannot be equal to positive 3. So when you graph this, this graph is going to be a line with a hole, okay? A hole in the middle of the line. Let's go ahead and bring in those graphs. So here you can see we have y equals x plus 3. That's just a regular straight line. We know the y-intercept is 3. We know it has a slope equal to 1. And this is the graph of that line. Over here we have the same line, right, as this line here, but you can see you have a hole in it. And the hole occurs at x equals 3. So just like we mentioned over here, since x cannot be equal to 3, there is no function value here at 3. Okay, and that's because if you try to plug 3 into this function, you will get division by 0, which is undefined. Now let's graph a slightly different rational function. So here we have the function f of x is equal to 6 divided by x minus 2. And you should see right away that x cannot be equal to 2. But this function is not going to simplify, right? It's a little bit different than the last example. So in this case, we're not going to have a hole in our graph. It's going to be a little bit different. What we're going to do is we're going to draw our x and y axis here. And at x equals 2, which is right here, we are going to put a vertical line. And it's a vertical dotted line. And that's representing the fact that x cannot be equal to this number. So whatever the graph does, it can't cross over this line. It can't go through this line. So this line here is what we call a vertical asymptote. And what's going to happen is as we plug in values of x that get closer to this line, you're going to see the function is either going to go this way toward that line or it's going to go this way toward that line. And the same thing happens over here on the other side. So to see this in action, what you really have to do is plug in some values. So here I have my x and my f of x. And again, I know I can't plug in 2. So what happens if I plug in numbers close to 2? Like what happens if I plug in x equals 1.9 and x equals 2.1, right? If you plug in 1.9, the function value at 1.9 is going to be 6 divided by 1.9 minus 2. And this is 6 divided by negative 0.1. And 6 divided by negative 0.1 is actually negative 60. F of 2.1 is going to be 6 divided by 2.1 minus 2. This is 6 divided by 0.1. And this is positive 60. So when I plug in 1.9, which is really close to 2, but on the left side of 2, I'm getting a really big negative number. It's way down here somewhere. And when I plug in positive 2.1, which is on the right side of 2, I'm getting positive 60, which is way up here. So to get the full effect of what this graph looks like, what you'll need to do is plug in some additional points. But I plug in these two values because I just wanted to see which way is it going as we get closer to that asymptote. So here is a table that has a little bit more detail. So you can see at x equals 2, y is undefined. And then I'm plugging in numbers to the left of 2 over here. So x equals 1, x equals 0, negative 1, negative 4. And I'm also plugging in x equals 3, 4, and 5. And when you plug those numbers in, you get these values. And when you graph those points, you can see, for example, the point negative 4, negative 1 is right here. Negative 1, negative 2 is here. 0, negative 3 is here. 1, negative 6 is down here. And remember, when I plugged in 1.9, it was way down here at negative 60. So you can see the behavior of this function as it gets close to that asymptote is it gets closer and closer to it, but never touches it, right? So this asymptote goes down here indefinitely, and the graph here just gets closer and closer to it. And of course, the same thing happens on the other side. Okay, so over here, as we get closer and closer to it, the graph is going up like this. All right. Now, another thing that's happening here is as you plug in larger values of x, if you were to plug in more values into this table, you would see the graph of this function coming down here, but never crossing the x-axis. And the same thing happens on the other side. It rises up here, but never crosses the x-axis. And that's because there is also a horizontal asymptote. And so this line right here, the x-axis, which is y equals 0, is what is known to be a horizontal asymptote. And it's very common to have vertical and horizontal asymptotes when you have rational functions. Now, it doesn't happen every time, as you saw in the previous example, but most of the time we do have these horizontal and vertical asymptotes. So let's consider g of x equals 6 divided by x plus 2. So once again, we know that in this case, x plus 2 cannot be equal to 0, right? Because that's the denominator. And so that means x cannot be negative 2. So when I go to graph this, we are going to have a vertical asymptote at x equals negative 2. So that looks something like this. And then we just need to plug in a few points to the left of negative 2 and to the right of negative 2 to see how the function is behaving. Now, this is pretty much just like the last problem, except that now our asymptote is at negative 2 instead of positive 2. So the behavior is going to be very much the same. So you can pause the video if you like, and you can plug in some values to the left of negative 2 and to the right of negative 2. You can see that I've taken the liberty to bring in the graph here, okay? But you can see that the behavior is very similar. It's going up, getting closer to that asymptote on this side. It's going down, getting closer to that asymptote on the other side, and then it's leveling out as x gets larger this way, and it's leveling out as x approaches negative infinity in the other direction. So let's go ahead and talk a little bit more about horizontal asymptotes. So remember, vertical asymptotes are where the function is undefined, right? It's where the denominator is 0. Horizontal asymptotes are a little bit trickier. A horizontal asymptote for the graph of a rational function is the horizontal line that the graph approaches as x takes on extreme values. The horizontal asymptote for the rational function f of x equals p of x over q of x will occur at the x-axis whenever the degree of p of x is less than the degree of q of x, or it will be the line y equals a divided by b, where a is the leading coefficient of p of x and b is the leading coefficient of q of x. And that's when the degree of p and q are equal. Now, I know that sounds kind of complicated, but we'll do an example here in just a minute. And then as a guide for graphing rational functions, you always want to go ahead and find your intercepts. So that would be x and y intercepts, if they have any. And you want to find the vertical asymptotes. You want to find the horizontal asymptote. And then you need to fill in the gaps with table values, right? So you need to pick values of x that are around those vertical asymptotes and then draw a smooth curve. So for example, the rational function y equals x minus 4 divided by x minus 2. So let's go ahead and talk about the x-intercepts. To get the x-intercepts, you let y equal 0. When you let y equal 0, you get 0 equals x minus 4 over x minus 2. And the only way a fraction can equal 0 is if the numerator of the fraction is equal to 0. And so that's going to be x equals 4. That's our x-intercept. For the y-intercept, we simply let x equal 0. And we're going to get y equals 0 minus 4 divided by 0 minus 2. This is negative 4 divided by negative 2, which is positive 2. So y equals 2 is our y-intercept. Next, let's go ahead and talk about the asymptotes. So the vertical asymptote. This is going to happen whenever the denominator is 0, as long as you can't simplify this. X minus 2 clearly equals 0 when x equals 2. And then the horizontal asymptote is going to occur when? So what was the rule for horizontal? Remember, it said if the degree of the top is equal to the degree of the bottom, which is the case here, then you take the leading coefficient here divided by the leading coefficient here. So in this case, the horizontal asymptote is going to be y equals 1 divided by 1, which is 1. So y equals 1 is our horizontal asymptote. So now what does that mean? Well, if we put all this together, we can start to see a rough picture of how this function is going to look. So here I have my x-axis, y-axis. I always like to do my asymptotes first. So x equals 2 is our vertical asymptote. Y equals 1, which is right here, is our horizontal asymptote. And then we know that the x-intercept was x equals 4. So that means it's going to cross the x-axis at x equals 4. We'll put that point right there. And it crosses the y-axis, right? The y-intercept is y equals 2. So on the y-axis, y equals 2 is right there. And that's where it crosses. Now, we still have to get more points, right? So we still have to plug in some values to the right of 2 and to the left of 2. And if you do that, you should see that the graph comes in something like this here on the right side. And on the left-hand side should do something like this here. And here is a better picture for that. So again, you can see you have your vertical asymptote here at x equals 2, horizontal asymptote at y equals 1, and then we have our x-intercept, y-intercept, and if you plug in and get a few more points, you can sketch the graph of that function. So for our next example, graph the rational function below. Again, show all intercepts and asymptotes. So if we find the x-intercept, remember we're just going to take the top of the fraction here, set that equal to 0. That gives us x equals negative 2. To get the y-intercept, we're going to let x equal 0. So y will be 0 plus 2 divided by 0 minus 3, which is negative 2/3. To get the vertical asymptote, remember that happens when you take the denominator and you set it equal to 0, and that gives us x equals 3. And for the horizontal asymptote, we have to look at the powers of each of those polynomials. And you can see that the power of the numerator is 1, the power of the denominator is 1, and each of those leading coefficients is also 1. So this is very much like the last problem. The horizontal asymptote is y equals 1 divided by 1, which is 1. And now we're just going to sketch this graph. Vertical asymptote is x equals 3. It's right here. Horizontal asymptote is y equals 1, which is right there. We have an x-intercept of x equals negative 2. That is right there. Y-intercept of y equals negative 2/3. So here's negative 1. Negative 2/3 is right about here. And you can see from this alone, I can get the idea that on this side, the graph must look something like this. So now to get the graph on the other side, all I need to do is plug in a few values. So for example, let's go ahead and plug in x equals 4. Y is going to be 4 plus 2 over 4 minus 3, which is 6. So x equals 4 gives us y equals 6. That's up here. And let's plug in x equals 5. If we plug in 5, we're going to get 5 plus 2 divided by 5 minus 3. This is 7 over 2, which is 3.5. So when I plug in 5, we're getting 3.5. So just from those 2 points alone, I get the idea that on this side, the graph is going like this. All right, so for this next one, a little bit more complicated denominator here. Graph this rational function. So again, to find the x-intercepts, you're just going to let y equal 0, which means just take the top of the fraction and set it equal to 0. For the y-intercept, we let x equal 0. Y is going to be 0 divided by 0 squared minus 9, which is 0. For the vertical asymptote, we're going to take the denominator here, which is x squared minus 9. Let's set that equal to 0. Now you can do this two ways. If I factor, I get this, and I can see the solutions are x equals 3 and also x equals negative 3. And for the horizontal asymptote, a little bit different this time, the power in the numerator is 1, the power in the denominator is 2, which is bigger. So in this case, the x-axis, which is y equals 0, is our horizontal asymptote. So when I go to graph this, I have a vertical asymptote at x equals 3, a vertical asymptote at x equals negative 3, okay. I have a horizontal asymptote, which is the x-axis, which is right here. And then I have some points. My x-intercept is x equals 0. My y-intercept is y equals 0, which is the same point. And you can see that there's still quite a bit that we don't know about this graph. So to better understand this graph, we need to plug in some values, get some numbers here. So let's remember our function is right here. It's x divided by x squared minus 9. And I'm going to plug in some numbers to the right of 0, so like 1 and 2, and also negative 1 and negative 2. So let's go ahead and plug those in. If x equals 1, we're going to get 1 divided by negative 8, which is negative 1/8. If x equals 2, we're going to get 2 divided by negative 5, which is negative 2/5. If x equals negative 1, we're going to get negative 1 over negative 8, which is positive 1/8. And if x equals negative 2, we're going to have negative 2 divided by negative 5, which is positive 2/5. Now, you could also plug in some numbers getting a little bit closer to 3. So if you really wanted a good idea here, you could plug in 2.5 or 2.9, also negative 2.5, negative 2.9. But from these here, I think I can get a reasonable idea of what's happening. So at 1, we're at negative 1/8. At 2, we're at negative 2/5. At negative 1, we're at positive 1/8. And at negative 2, we're at positive 2/5. And if you plugged in some points a little bit closer to those asymptotes, what you would see is that this turns around here and goes down that way, and this one turns and goes up this way, okay? And then for the sections of the graph out here, same idea. We're going to want to plug in a few more values. So let me plug in some numbers out here, like maybe x equals 4 and x equals 5. If I plug in 4, I get 4 divided by 16 minus 9. That's 4/7. If I plug in 5, I get 5 divided by 25 minus 9, which is 5/16. So when I plug in 4, I'm getting 4/7, and then I'm getting 5/16, which is a little bit lower. So what's happening here is this is getting close here, and right at x equals 3, of course, it's going up like this. And then I'll let you do this part, but if you plug in x equals negative 4 and negative 5, you will see that you get this behavior. And this is a pretty complicated rational function to graph. But once you have the basic characteristics, the intercepts and the asymptotes, it can help guide the process. And for our last problem, we'll do an application of rational functions. So Math TV decides to sell t-shirts to use for advertising. They make an initial investment of $100 to pay for the design of the t-shirt and to set up the printing process. After that, the t-shirts cost $5 each for labor and materials. Okay, so In part A, they say express the average cost per t-shirt as a function of the number of t-shirts that they produce. All right, so to understand this, let's first just talk about what is the cost to produce a t-shirt if the number of t-shirts is X. How much does it cost to make X t-shirts? Well, you're going to have to pay $100 just to get the t-shirt set up, to design it, etc. And then you're going to pay $5 each for every t-shirt that you actually produce. So the cost is going to be $100 plus $5 times X. Okay? But in part A, they want the average cost. So what is the average cost? Well, the average of anything is the total amount divided by the number of things. So the average cost per t-shirt is going to be the total cost to produce X t-shirts divided by the number of t-shirts, which is X. So this is our average cost function. Now for part B, it says make a table of values for the function. Now, if you think about it, it doesn't make sense for X to be equal 0, right? We're not making 0 t-shirts. And it also doesn't make sense for X to be a fraction because X has to be the number of t-shirts. So the only kinds of values that I'm going to plug in here are going to be whole numbers. So I can make 1 t-shirt, I can make 2 t-shirts, I can make 5 t-shirts, 10 t-shirts, 20 t-shirts, etc. So let's go ahead and plug these in to see what we get. So the average cost, and I'll just call this A for average. The average cost when X is equal to 1 is going to be 100 plus 5 times 1 divided by 1, and this is going to be 105. So if you only make 1 t-shirt, the average cost is $105. Okay, but what happens when you make 2 t-shirts? Now the average cost is 100 plus 5 times 2 divided by 2. And this is 110 divided by 2, which is 55. So notice that the average cost comes down significantly when you make more. If you make 5 t-shirts, the average cost is going to be 100 plus 5 times 5 divided by 5. And this is 125 divided by 5. And this equals 25. So if you make 5 t-shirts, the average cost is $25 per shirt. What if you make 10 t-shirts? Well, here the average cost is going to be 100 plus 5 times 10 divided by 10. This is 150 divided by 10, which is $15. So you see, the more t-shirts you make, the less it costs per t-shirt. If you make 20 t-shirts, the average cost is going to be 100 plus 5 times 20 divided by 20. This is 200 divided by 20, which is 10. All right. Now, if you go to graph this, what you're going to see is that when you make 1 t-shirt, it's a very, very high number. When you make 2 t-shirts, it's a little bit lower, etc. But it's really not until you get to like 5 t-shirts where now the cost is $25. At 10 t-shirts, the cost is $15. At 20 t-shirts, the cost is $10. And so what you can see is that you have this function that's going something like this. Right? It's coming down and it's getting closer and closer here. And that's because we have a horizontal asymptote going across here, right? And what is that horizontal asymptote? So to get the horizontal asymptote, remember this is x to the 1, x to the 1. What you do is you take the leading coefficient here divided by the leading coefficient here. And 5 divided by 1 is 5. And so the horizontal asymptote is going to be here at y equals 5. And that comes across like this. Now, why is that the horizontal asymptote? Well, remember, that was the cost per t-shirt after you got it all set up. So when you make a lot of t-shirts, the average cost of that t-shirt is going to approach the price per t-shirt that you saw up here, the $5 each, right? Because the initial $100 that you paid to get everything set up, that starts to diminish as you make more and more t-shirts. So this is an important concept to understand. Like if you're going to start a business or something like that, you're going to have some kind of a cost up front. You have to buy machines or things, stoves, whatever, refrigerators if you're running a restaurant. So you have an upfront cost, and that costs a lot of money initially. But as you make more of the product and you sell it, that initial cost diminishes over time. And that concludes this video lesson.